Welcome to Irodov problem solving series, and this is problem number 2.11 in heat and thermodynamics segment. This time the problem is stating find the maximum attainable temperature of ideal gas in each of the following processes. The first process being P equals P naught minus alpha V square, and the second process being P equals P naught e to the power minus beta V, where P naught, alpha and beta are positive constants and V is volume of 1 mole of a gas. So what is interesting to note over here is that in both the problems the amount of gas is going to be 1 mole. So in the first problem, to calculate the maximum attainable temperature, the process equation that is given to us is P equals P naught minus alpha V square. So as we can see that there is no temperature term associated over here, and I have always mentioned whenever you are solving a problem and it is stated over there that we are dealing with an ideal gas, so always remember that you have another alternate equation available to you all the time, that is PV equals nRT. So in this case, since we are dealing with 1 mole of the gas, we can definitely write from here that temperature T can be written as PV by R. So this alternate equation is always available all the time. And now if we substitute the value of P from the given equation, then we can write that therefore temperature T can be expressed as P naught minus alpha V square times V divided by R. So this is the expression for temperature that we have. And now we can maximize the temperature over here in this expression to get the maximum attainable temperature. So now to calculate the value of maximum temperature, that is for T to be maximum, we will calculate dt by dv and equate this value to 0. So to calculate dt by dv and then equate this value to 0, so we are writing it as P naught by R dv by v minus alpha by R derivative of v cube by v, and then we equate this equal to 0. So we are technically differentiating this term P naught V by R minus alpha V cube by R. So we are differentiating this term and equating to 0, and on derivative we obtain this value as P naught minus 3 alpha V square equal to 0, and from here we obtain the value V equals root over P naught by 3 alpha. So this is the condition that we obtain by differentiating the value dt by dv and equating it to 0. That is, we are applying the condition for maxima. Now if we check the second derivative, so this is the first derivative that we have. If we check the second derivative, that is d square t by dv square, that is d square t by dv square. So if we are calculating the second derivative, so on calculating the second derivative, we are getting the value minus 6 alpha v. If P naught is a constant, then we are getting the value minus 6 alpha v, and that is, we can say that this value is turning out to be negative. This value is turning out to be negative. Hence, the condition which we have obtained must be positive. So this comes out to be negative. So therefore, v equals root over P naught by 3 alpha is the condition for temperature to be maximum, and hence if we put this value over here, then we get the maximum temperature condition. Therefore T maximum turns out to be 2 by 3 P naught by R times of root over P naught by 3 alpha. So this is the first part of the problem which we have solved. This is the part A of the problem. In the part B, again we will be repeating the same process. This time the only difference is the process equation. So this is the first part of the problem which we have. Now we are moving to the second part of the problem. So for the second part of the problem, that is B part of the problem, we have the expression P equals P naught e to the power minus beta v. So again I have already mentioned that we already have an alternate expression, that is from T equals PV by R. So if we substitute the value of P over here, then we get the expression P naught V e to the power minus beta V by R. And now for T to be maximum, for temperature to be maximum, we want dt by dV to be equated to 0. So for dt by dV to be equated to 0, so we get, therefore P naught by R is constant. So we will be applying product rule. So first we will be keeping e to the power minus beta V constant, and we are differentiating V with respect to V, and then we are keeping V constant and we are differentiating e to the power minus beta V with respect to V, and then we are equating this entire value to be equal to 0. So over here on solving, we obtain P naught by R e to the power minus beta V dV by dV being 1 plus V minus beta e to the power minus beta V, and this value is equated to 0, and on solving we obtain V equals 1 by beta. Now similar to the above expression, we can write over here that d square T by dV square is turning out to be negative, hence this is the condition for temperature to be maximum. This is condition for temperature to be maximum, and on substituting the value we get maximum temperature value as P naught by E beta R. So this is the second part of the problem which we have solved. So these are the two problems which were discussed over here, and we were asked to calculate maximum attainable temperature. So this was problem number 2.11.